Section 16.8, Relationship between K sub A and K sub B. We've seen in a qualitative way that the stronger acids have weaker conjugate bases. To see if we can find a corresponding quantitative relationship, let's consider ammonium and ammonia conjugate acid-base pair. Each of these species reacts with water. Ammonium reacts with water to form ammonia and protons. Ammonia reacts with water to form ammonium and hydroxide. Each of these equilibria is expressed by a characteristic dissociation constant. K sub A is the concentration of ammonia times acid divided by ammonium. K sub B is ammonium times hydroxide divided by base. When equations 16, 38, and 39 are added together, the ammonium and the ammonia species cancel, and we're left with just the autoionization of water. Recall that when the two equations are added together to give a third, the equilibrium constant associated with the third equals the product of the equilibrium constants of the two added together. Applying this rule to our present example, when we multiply K sub A and K sub B, we obtain the following: K sub W. Thus, the result of multiplying K sub A times K sub B is just the ion product constant of water, K sub W. We expect this result because adding equations 16, 38, and 39 give us the autoionization equilibrium for water, which is the equilibrium constant is Kw. This relationship is so important that it should receive special attention. The product of the acid dissociation constant for an acid and the base dissociation constant for its conjugate base equals the ion product constant for water. Ka times Kb equals Kw. As the strength of an acid increases, the larger the K sub A, the strength of the conjugate base must decrease, smaller K sub B, so that the product K sub A times K sub B equals 1 times 0 times 10 to the negative 14 at 25 Celsius. The Ka and Kb data in Table 16.5 demonstrate this relationship. Remember, this important relationship applies only to the conjugate acid-base pairs. By using equation 1640, we can calculate K sub B for any weak base if we know K sub A for its conjugate acid. Similarly, we can calculate K sub A for a weak acid if we know K sub B for its conjugate base. As a practical consequence, ionization constants are often listed for only one member of a conjugate acid-base pair. For example, Appendix D does not contain K sub B values for the anions of weak acids because they can be readily calculated from the tabulated K sub A values for their conjugate acids. If you look up the values of acid-base dissociation constants in a chemistry handbook, you will find them expressed as pK sub A or pK sub B, that is, as the negative log of K sub A or the negative log of K sub B. Equation 640 can be written in terms of pK sub A and pK sub B by taking the negative log of both sides.